I hope all of you are doing good. Let's start today's chapter, circles. Introduction. In our previous classes, we have learned about circles and related concepts. In this chapter, we shall learn some more properties of circles. These properties are related to perpendiculars from the center to a chord, angles subtended by chords, and arcs at the center or a point on the circle, and angles of a cyclic quadrilateral. Okay, a brief review. What is circle? Actually, it is a set of those points on a plane that are at a given constant distance from a given fixed point in the plane. The distance from the fixed point is the radius of the circle. 2. Diameter. A line segment passing through the center of the circle and having its endpoints on the circle is called a diameter of the circle. 3rd, chord. A line segment joining any 2 points on a circle is called a chord of the circle. Remember, diameter is also a chord. Okay. 4. Semicircle means half of the circle. A diameter of a circle divides the circle into 2 equal parts. Each part is called a semicircle. For example, this is a circle, this is the diameter. Okay, so this diameter is dividing this circle into 2 circles, 2 half circles. Secant. A secant is a line segment that intersects a circle at 2 points. 6. Circumference of a circle. The perimeter of a circle is called its circumference. 7. Length of an arc. It is the length of that part of circumference covered by the arc. 8. Major arc. The arc of a circle is called a major arc if its length is greater than the length of a semicircle. 9. Minor arc. An arc of a circle is called a minor arc if its length is less than the length of the semicircle. 10. Central angle. An angle with its vertex at the center of the circle and 2 radii drawn from the endpoints of an arc as its arms is called the central angle of the arc. 11. Degree measure of an arc. The degree measure of an arc is the measure of its central angle is degree. The degree measure of an arc, PQ, is denoted by this symbol. Okay. Next is congruent arcs. 2 arcs of a circle are congruent if either of them can be superposed over the other so as to cover it exactly. Next, sector of a circle. A sector of a circle is a region enclosed by an arc of the circle and the radii of its endpoints. And next, segment of a circle. The segment of a circle is a region bounded by an arc of the circle and the chord joining the endpoints of the arc. Now, properties of chords of a circle. We shall now learn some properties of chords of a circle. These properties can be verified experimentally. However, for clarity, the proofs of these properties are given below. Property number 1. The perpendicular from the center of a circle to a chord bisects the chord. Okay, as you can see. So, let PQ be a chord of a circle with center O and OL is perpendicular to PQ. Now, we can join OP and OQ. In triangle, right triangle OLP and OLQ. See, these 2 angles are 90 degree. Okay, OP is equals to OQ. OP is equals to OQ because these 2 are radii. Okay, and OL is equals to OL, common. Therefore, these 2 triangles are congruent. Therefore, PL is equals to QL because congruent part of congruent angles. Therefore, OL bisects PQ. Property 2, this is the converse of property 1. The line joining the center of a circle to the midpoint of a chord is perpendicular to the chord. Proof. Let PQ be a chord of a circle with center O. Let M be the midpoint of PQ, join OM. In triangle OMP and OMQ, OP is equals to OQ. These are radii. OM is common. PM is equals to QM. M is the midpoint of PQ. Therefore, OMP, triangle OMP is congruent to OMQ by SSS property. Angle PMO is equals to angle QMO is equals to 90 degree. Since angle PMQ is equals to 180 degree, OM is perpendicular to PQ. Property 3. In a circle, equal chords subtend equal angles at the center. Let AB and CD be 2 equal chords of a circle with center O and radius R. So, we need to prove that angle AOB is equals to angle COD. In triangle AOB and COD, OA is equals to OB is equals to OC and OD is equals to R because all are radii. Okay, and AB is equals to CD, it is given here. Therefore, these 2 triangles are congruent and therefore, these 2 angles are also congruent by CPCT, that is corresponding parts of congruent angles are equal. Now, property 4, which is converse of property 3. In a circle, chords which subtend equal angles at the center are equal. Okay. Now, proof, let AB and CD be two chords that subtend equal angles at the center. Now, in triangle AOB and COD, okay, these fours are sides, so these are radii, so these are equal. Also, angle AOB is equals to COD, this is given, and therefore, these two triangles are congruent by SAS property. Therefore, AB is also equals to CD. Now, property 5, equal chords of a circle are equidistant from the center. Okay. So, these two are the equal chords of a circle. Proof, let AB and CD be two equal chords of a circle with center O as shown in this figure. Now, we will join O and OC. Draw OM perpendicular AB and ON perpendicular CD. We need to prove OM is equals to ON. Okay. Now, proof, since perpendicular from center bisects the chord, therefore, AM, that is AM, is equals to what? Half of AB, right? AM is half of AB. Similarly, CN is half of CD. No. But you know, AB is equals to CD because these two chords are equal, right? Therefore, AM is also equals to CN. Okay. Now, in triangle AMO and CNO, AM is equals to CN. Here we have proved, okay, and you know, OM is perpendicular to AM and ON is perpendicular to CN. OA and OC, these two are radii. Therefore, triangle OMA is congruent to triangle ONC by RHS congruence part. Therefore, OM is equals to ON. And corresponding parts of congruent triangles and AB and CD are equidistant from O, hence proved, right? Next, property 6, chords of a circle which are equidistant from the center are equal. Proof, let AB and CD be any two chords of a circle with center O such that they are equidistant from O. That is, OM is equals to ON, where OM is perpendicular to AB and ON is perpendicular to CD. OM is perpendicular to AB and AM is equals to half of AB. ON is perpendicular to CD and CN is equals to half of CD. Perpendicular from the center bisects the chords. Okay. Now, we will join OA, OC and OA. OC is equals to OA, OC is equals to OA because these two are radii. Now, in right triangle OMA and ONC, OA is equals to OC radii, OM is equals to ON, it is given, and also these two angles are equal, that is 90 degree. Therefore, by RHS congruency property, these two triangles are congruent. Okay, and by CPCT, AM is equals to CN, and half of AB is equals to half of CD. That therefore, AB is equals to CD. That means chords of a circle which are equidistant from the center are equal. Okay, now let's do some examples. Example number 1. In a circle of radius 13 centimeter, a chord at a distance of 5 centimeter from the center. Find the length of the chord. Okay. See, this is AB is the chord of a circle, radius is a 13 centimeter at a distance of 5 centimeter from the center. OA is 13, OM is 5. Now, we will use Pythagoras theorem here. So, OA square, this is the hypotenuse. OA square is equals to OM square plus AM square. Okay. OA is a 13 square, OM is 5 square plus AM square. We don't know the length of AM. Square of 13 is 169, 25 plus AM square. 169 minus 25 is equals to AM square. 144. You know, 144 is the square of 12. So, the length of AM is 12 centimeter. But wait, we have to find the length of the chord AB. So, AB is the twice of AM. Therefore, AB is equals to 2 into 12, that is 24 centimeter. Okay. Exercise 25.1. In a circle of radius 10 centimeter, a chord is at a distance of 6 centimeter from the center. We have to find the length of the chord. Okay. Let AB be the chord of the circle. O is the center. This is the radius. Okay. Radius is 10 centimeter and the chord is a distance of 6 centimeter. Okay, this is C and this is D. Okay, now we have to find the length of the chord. So this is similar to the example number 1. Okay, so here as you can see, AD, this is a smaller side, AD square is equals to AC square minus CD square. Okay, 10 square minus 6 square. 100 minus 36 is 64. Okay, and 64 is the square of 8. So the length of AD is equals to 8 centimeter, but we have to find the length of the chord AB. AB is twice of AD, so length of AB is 2 into 8, that is 16 centimeter, right? Angles subtended by an arc at the center and at any point on the remaining part of the circle. Let us consider an activity. Draw a circle with center O. Take an arc and mark a point C on the remaining part of the circle. Join OA, OB, CB and C. Repeat this activity by drawing 2 more circles with the different radii. Label the figures similarly and number them 1, 2 and 3. We then record the observation on a table as shown below. Okay. So what do you observe here? We observe that in each case angle AOB is equals minus 2, angle ACB is 0, so small that it may be ignored. This activity shows that the angle subtended by an arc of a circle at the center of the circle is double, and the angle it subtends on the remaining part of the circle. Okay. Example 1. In the figure, ABCD is a square. Okay, as you can see, this is a square inscribed in a circle with center O. Find angle AOB. Okay, this angle BOC, this one, COD, this one, and DOA. We have to find all the 4 angles of a square. Okay, so how will we find? See, all 4 sides are equal because sides of a square are equal. And angle AOB is equals to BOC is equals to COD is equals to angle AOD, that is 360 by 4, that is 90 degree. Okay, so equal chords subtend equal angles at the center. Right? Example 2. In the given figures, point O is the center of the circle. Okay, we have to find the value of x. Value of x is what? Double of this angle, that is 60 degree. And here, value of x is what? Half of this angle, that is 60 degree. Okay. Exercise 25.2. An equilateral triangle ABC is inscribed in a circle with center O. Find the measures of angle POC, angle COA, this one and this one. Okay. Now you know that an equilateral triangle has all 3 sides equal. Okay, and all angles are of 60 degree. This is 60, this is 60, and this is also 60. Now, if this angle is 60, then this angle will be 120 degree. Okay. Similarly, this is 60 degree, then this angle will be 120 degree. So all 3 angles will be 120 degree each. Right? The reason is given here. Next, cyclic quadrilateral and its angles. Cyclic quadrilateral. A quadrilateral is called a cyclic quadrilateral if all its vertices lie on a circle. Property 1. In a cyclic quadrilateral, the sum of each pair of opposite angle is 180 degree. All opposite angles of a cyclic quadrilateral are supplementary. Proof. Let ABCD be a cyclic quadrilateral. See, this is the cyclic quadrilateral because all the 4 vertices are lying inside the circle. Okay. So, ABCD is a cyclic quadrilateral inscribed in a circle with center O. Then we have to prove that angle B plus angle D is equals to 180 degree. Opposite angles, okay, and angle A plus angle C is equals to 180 degree. Proof. Consider side AB, okay, this side AB of quadrilateral ABCD as the chord of the circle. Clearly, angle ACB and angle ADB are angles in the same segment determined by the chord AB. Therefore, ACB is equals to angle ADB. Next, we consider side BC of quadrilateral ABCD as the chord of the circle. We observe that angle BAC and BDC are angles in the same segment. So, angle BAC is equals to BDC, okay, adding 1 and 2, what will we get? ACB plus BAC is equals to ADB plus BDC is equals to angle ADC. And adding ABC on both sides, what will we get? Angle ABC plus ACB plus BAC is equals to angle ADC plus angle ABC is equals to 180 degree is equals to angle ABC plus angle ADC. Sum of angles of a triangle is equals to 180 degree. Angle B plus angle D. But angle A plus angle B plus angle D plus angle C is 360 degree and A plus C is equals to 180 degree. The converse of the above property is also true. Property 2, if a side of a cyclic quadrilateral is produced, then the exterior angle is equals to the interior opposite angle. Proof. See, let ABCD be the cyclic quadrilateral and side AB be produced at E. Then we have to prove that angle CBE is equals to angle ADC, that is this angle. So, since sum of opposite angles of a cyclic quadrilateral is 180 degree, we have angle ABC plus ADC, means this sum of this angle and this angle is 180 degree, and ABC plus CBE is equals to 180 degree because these two form a linear pair, right? So, angle ABC plus angle ADC plus angle is equals to angle ABC plus angle CBE. See, angle ABC plus angle ADC is equals to angle ABC plus angle CBE, right? Now, angle AD, okay, these two angles will cancel out and angle ADC is equals to angle CBE, okay? Or you can also write like angle CB is equals to angle ADC. Now, let us consider some example. Example 1. In the figure ABCD is cyclic quadrilateral. If angle A is 75 degree and angle B is given here, we have to find angle C and angle D. So, angle B plus angle D is equals to 180 degree. Angle B plus angle D is equals to 180 degree. Angle B is given 100 degree. Angle D is 180 degree minus 100 degree, that is 80 degree. Similarly, angle A plus angle C is equals to 180 degree. Okay, and angle C is equals to 180 minus 75 degree, that is 105 degree, right? Let's do exercise 25.3. In the figure, ABCD is a cyclic quadrilateral with angle A is equals to 80 degree and angle B is equals to 70 degree. We have to find C and D. Okay, angle A plus angle C is equals to 180 degree. Angle A is given, which is 80 degree. Angle C we have to find. Angle C is equals to 180 degree minus 80 degree, that is 100 degree. Okay. Now, angle B plus angle D is 180 degree. Angle D is 180 minus angle B. Angle B is given 70 degree. Okay, and angle D is equals to 110 degree, right? Things to remember. Number 1, in a circle perpendicular from the center to a chord bisects a chord. 2, in a circle the line joining the midpoint of a chord to the center is perpendicular to the chord. 3, equal chords of a circle are equidistant from the center. 4, chords equidistant from the center are equal. 5, equal chords of a circle subtend equal angles at the center. 6, chords of a circle which subtend equal angles at the center are equal. 7, angles subtended by an arc at the center is double the angle subtended by it on the remaining part of the circle. 8, the angle subtended by an arc at the center is called the central angle of the arc and the arc is called the intercepted arc corresponding to the central angle. 9, if all the 4 vertices of a quadrilateral lie in a circle, it is called a cyclic quadrilateral and the 4 vertices are called concyclic points. 10, opposite angles of a cyclic quadrilateral are supplementary. Remember this line. Okay, students. Now, you will do practice of the remaining questions of this chapter.